Okay. Okay. Science time today. We're talking about magnets, but first it says the bell work reads. Oh, also I forgot to mention this is spooky. You can notice it's dark and spooky. Also, it'll make it really inconvenient for Teague and whoever else watches this to see anything because it's so spooky that you can't see it. You can kind of see it though, right? I can't see it from here, but you can basically make out what's going on. Let's turn the light on, Ada. I think it'd be more evil. It's really nice to have the vibe of spooky Halloween, but it would be nicer to actually be able to learn. I already took some ibuprofen, so I'm not going to get a headache from that. The bell work reads, in a paragraph, explain how magnets exert a force. Use your explorations in lab as sources. So I want someone, you don't have to say your whole paragraph, but I would like a volunteer to tell me how, in your words, magnets exert a force. Maybe let's just start with that. Magnetism is in itself a force. It's one of the four what we call fundamental forces, but it's related to the force of electromagnetism, or the electromagnetic force. What other phenomenon do you think is contained within the electromagnetic force besides magnetism? Besides magnetism, what other force is contained within electromagnetism? Isaiah? Electricity, yeah. So this force, the discussion we will have throughout this discussion and the next will encompass, and I think one more after that too, will encompass both electricity and magnetism. Electromagnetism is the fundamental force that relates both of those things. But anyway, how, the bell work says, do magnets exert a force? Call for volunteers. I wondered if it was going to be you. Let's hear it.
Would it be like a push or pull?
Okay, yeah. A force, as we've said before, is a push or pull. Here's a pretty good example. Do you see this little guy?
Yes.
Great answer. You do see this little, if you turn around, even those of you dressed as Soldier Boy, if you turn around, you will see this little guy. And I'm doing this, but even when I'm not doing that, if you can still see it, is it right now exerting a push or a pull?
Yes.
Yeah. Remember, things don't have to, another way of saying that is it still exerting a force? And things don't have to be moving in order to exert a force. That a force, an unbalanced force, causes a change in motion, but not every force is unbalanced. If you had to guess, what is this force balanced by? Okay, the whiteboard is the object. Yeah, what force balances the force of magnetism in this case? The whiteboard is doing it, but I think we would still call it the normal force. It's just the push, it's the resistance of the whiteboard. Because magnetism works kind of similarly. In fact, in a lot of ways, it is very similar to gravity. We've talked about gravity before. There are some differences, but I'm going to give you a real brief little math here that you're going to love about math. But the force of gravity, F sub g, if you remember, equals the gravitational constant times the two masses multiplied divided by the distance between them. You probably remember that. I mean, this should be in your discussion from gravity. The force of electromagnetism is equal to the electromagnetic constant times the two charges multiplied divided by the distance between them. So these two, you can see these two equations are similar. The reason this is fast is because you don't actually need to do the math with this yet. We will do the math with this one next year. You don't need to worry about either of these. What I'm trying to demonstrate to you is that, do you see some similarities in this math? I hope that you know enough about how math works that you can at least see some similarities. Look at what we've got here. So in both of these calculations of force, right, we have two calculations for force. In each case, we have a constant. Fundamental forces of the universe are governed by these constants, multiplied by two different properties of matter, in this case mass, and in this case charge, and in both cases divided by the distance between them squared. I used colors. Do you see the similarities between them? Does anyone, raise your hand if you see some similarities between these two equations? Yeah, they're similar equations. I mean, they're not the same, but there are similarities between them because they're both fundamental forces of the universe. They're both pushes or pulls. And just like gravity attracts massive objects, magnetism is the attraction between objects that have a charge. But one key difference is there's another thing that magnets do. Unlike gravity, which attracts any objects with mass, in electromagnetism, it's not just attractive. You remember that? I hope you found that out in your lab. That was the second part of the bell work, is use your explorations and labs as sources. What in your lab did you find is true of magnetism? Where gravity can only attract things to our knowledge, magnetism can also do what? Push away. What's the word for push away?
Detract.
No. Good guess.
Untracked.
Untracked. No. Although I think you should coin that term for if you don't think one of your classmates is cute, you can say I'm unattracted to them. But don't, no, opposite of attract is not untracked. It is, you could also say this, but it sounds really mean if you say about a person. No, even worse. Yeah, repulse is exactly it. So if you okay, that's a pretty good example actually. If you we're not going to use your classmates as examples, but if you think of a person who is attractive to you, you know what that means. You're in 8th grade, so you know what that means. But you can also think of a person who is repulsive to you, and you know what that means. That these two things, even in our social interactions, are opposites. But they're also opposites in magnetism. So unlike gravity, this is the key here, unlike gravity, which is only attractive, magnetism, broader electromagnetism, can be attractive or repulsive. And how do we know if two charged particles are going to attract or repel? Well, here I have three sets. Here I have three sets of charged particles. Let's say these ones are positive. These ones are positive, and let's say these ones are negative. So in instance the first, what do you think is going to happen between these ones?
One is not going to attract
a little more specific. You're on the exact right track. You just haven't gone quite far enough. But we're just talking about instance 1 right now. What's going to happen in instance 1? They're going to repel. Yeah, there's a repulsive force between them. Like charges repel. So the verb is repel, to repel. These charges have been repelled. The adjective version of that is repulsive. So the force between them is repulsive. They have been repelled. What about in the second case? They attract. Oh, I've drawn arrows here on the edge. I should have done this in a different color. Opposites attract. You didn't even know that from, you've probably said that about one of your homies. I don't know. I'm going to erase these arrows because I don't want the arrows to seem, or I don't want that arrow to seem like it's out of place. So this is a real arrow, a force arrow. I'm going to put a colon instead. There we go. And then in the final example, similarly, doesn't matter what the charges are. If they're like, they repel. And if they're opposites, they attract. I mean, I guess in a sense, it absolutely does matter what the charges are. But when I say that, I mean both negative and positive repel. Okay, so all of that from Amelia's comment that when the question is, how do electromagnetic forces behave? One of the answers is they push or pull, as all forces do. And they can be, like all forces, balanced or unbalanced. Remember, we talked about that already. So in this case, the magnetic force on the whiteboard is balanced, and if I move it away a little bit, it's now unbalanced. You see, even as well, that was a pretty good one. Did you see that? even as I drop it, it's attracted to the whiteboard. So there's kind of a kind of complicated situation here where what's pulling it down, as we would say down? Gravity's pulling it down, but also because there's a magnetic attraction between the magnet and the whiteboard, it's also being attracted to the whiteboard. And so it ends up going at what we call the resultant of those two. It's going to go diagonally down and towards the whiteboard. So there is an unbalanced force acting on it. And then another complexity of this is that as it's falling, gravity would still pull it down, except for there's also friction. So we're dealing with three forces here, really, and in fact, even a fourth because of the normal force of the whiteboard resisting the magnetic force. So we have four forces acting on it: gravity down, magnetism in, I guess we'll say, normal force out, and friction up. Right, the friction's opposing the motion of gravity. So that's how our little magnet works. Why doesn't this repel though? How come? So this magnet just happens to be an opposite charge of the board? No, there are different kinds of magnetism. I want to use the same words as your book because I've made this mistake on videos in the past. Maybe it's not even yet. This might be something we talk about in lesson 3. If it is, we'll revisit that, but hold on just a second while I look. I found it. Okay, so I think your book refers to this as permanent and temporary magnets, but nope, it calls them ferromagnetic. Good. I'm glad to. I probably could have just asked you. You guys just did these explorations. The little succulent. This little drop it object is supposed to be a succulent. It's made of plastic, but this little succulent has in its pot what we call a ferromagnet. You've read that word in your explorations, but a ferromagnet, F-E-R-R-O magnet, a ferromagnet is one that has permanent, I'm going to put that in quotes, nothing lasts forever, permanent magnetic domains. And I'm going to underline magnetic domains. We'll come back and define those. But basically, this is generating its own magnetic field. It's generating its own magnetic field without regard for the magnetic fields of objects around it. A ferromagnet exerts a permanent magnetic field. Permanent in quotes, nothing lasts forever. So give me another example of a ferromagnet, something that generates its own magnetic field. Did you use one in your lab? The Earth behaves as a ferromagnet. It's a little more complicated than that, but that's a good example. What else did you use in your lab that was exerting its own magnetic field? A magnet, yeah. You in your life would just call this object a magnet. That's what it is. It's a magnet. A magnet, like a fridge magnet or a bar magnet, or you probably used a ring magnet in your lab, or maybe even a horseshoe magnet. But those things that we call magnets are ferromagnetic. They exert a magnetic field. And we'll talk about why they are in a second. But there's also temporary magnets. There's also temporary magnets where these things, let's say they respond, I think that's a good word, respond to an external magnetic field. Let me give you a simple example of this. Remember the word field is spelled F-I-E-L-D. I think I have a great example for this. So I have here my permanent magnet. Do you see a permanent magnet within the little pot? Hi. You see him? He's shiny. I'll go it like this so that you can see that it's shiny. Do you see the permanent magnet in there? Do you see it, Cash? Did you see that it sticks to the whiteboard? Let's see again. Oh, this is what you get for acting like an idiot, is that things break. But what's going on here? How come it doesn't stick to this? There's not a magnetic force coming from the whiteboard either.
There's no metal.
Okay, yeah, you're getting closer, but let me, does anyone have a paperclip? I do. Check this out. Here's how you can see, someone said there's a magnetic force coming from the whiteboard. Let me show you how that, you can tell that's not true. Here's a paperclip. You can see the paperclip is attracted to the permanent magnet, but it's not attracted to the whiteboard. So there's not a magnetic field coming out of the whiteboard, just like there's not a magnetic field coming out of the wall. But the whiteboard behaves as a temporary magnet. So it will respond to an external magnetic field. Where's the external magnetic field? Well, in that case, it's this. This thing, since it's a permanent magnet, exerts a force on this temporary magnet, and they stick together. This is not a temporary magnetic. I'm sorry, this is not a temporary magnet. So it doesn't. And in the same way, this little paperclip is only a temporary magnet. So this will respond to a magnetic field, but it doesn't exert its own magnetic field. Let's diagram what's going on here on the atomic level. I think that'll be the last thing we do. I'm going to come over here, and for you guys, my body's going to block this, and that you'll just have to get it in a second. So in this one, I'm going to have two kind of close-ups here. There are certain atoms, for example, iron, cobalt, and nickel. There are some others, neodymium, praseodymium, promethium. There are certain elements that can respond to a magnetic field. It has to do with the way their electrons, a subatomic. Have you ever heard of electrons? You guys did atoms last year in 7th grade science. So it has to do with the way their electrons are arranged and the way they spin. But basically, they can either be oriented, we call it north and south. For electricity, we call it positive and negative. In magnetism, we call it north and south, but there's a relationship between those. And in a ferromagnetic material, there are regions within it called magnetic domains that all are made of atoms, and within that magnetic domain, most, or on average, the atoms all point in the same direction. Does it kind of make sense if I say the atoms all point in the same direction? The way their electrons are spinning, the way their electrons are arranged, the north and south poles of those atoms all more or less point, on average, in the same direction. So even though there's some variance in them, on average, all of these arrows, all of these atoms are generally pointing which way? Yeah, up on our drawing. So because of the average of these magnetic domains, this exerts a permanent magnetic field. Now in this object, when I say this object, I mean the temporary magnet, it has those magnetic domains, and it has the kind of atoms that can align themselves to magnetic domains, but they're all kind of randomly arranged. So on average, how are these pointing? Well, not. They're kind of randomly arranged. But when this temporary magnet, the whiteboard, the paperclip, comes into the field of a permanent magnet, all of these line themselves up with the permanent magnet, and it attracts to it. Okay? The difference then with the wall or a marker or ya boy, the difference is that those materials are not largely made out of the kind of atoms that can behave in this way in a magnetic field. Okay? So those would be non-magnetic. I guess we could draw another one called non-magnetic, which I don't even need to define. You know what non means. Non-magnetic, a diagram of that would just be no magnetic domains at all. It's just atoms that do not orient themselves with a magnetic field. So atoms that are not iron, cobalt, or nickel. There are other elements too, especially that can be temporary magnets. So it all comes down to these magnetic domains, these regions of atoms that arrange themselves in a particular way. That's what causes the magnetic force. So do you have examples of this? Why are you talking? Do you have examples of this from your lab that you can give me? Did you guys do a lab about magnets? So someone raise your hand and tell me what you did about magnets in your lab. No one. It's always you. Not you. Trey.
Magnets, the direction of force based on the direction of the magnet.
Okay, so you had a permanent magnet that you got out of the box, and depending on how you arrange that magnet, it caused a difference in how objects were attracted to it. Is that correct? Or maybe even you had two magnets, and whether or not they attracted or repelled was based on their orientation. Yep, that's correct. Did anyone's lab deal with the distance away from a magnet that probably temporarily magnetic objects got? Like maybe someone had, at this distance, this many paper clips were attracted, and then we moved it further away and only fewer were attracted. Did anyone do that kind of lab? Because that has to do with this part of the equation where if we have the force of electromagnetism, it gets weaker the further away from a permanent magnetic field that it gets, right? So a magnet is strongest nearer the magnet. Like the magnetic field is stronger by it, and that's why the further away it gets, if I hold it out to here, the magnetic field is not strong enough to attract it back to the whiteboard, right? I'm going to break it if I drop it again. You can imagine. Oh. Whereas if I hold it closer, it will. I want it to be close enough that it does grab on or does attract, but far enough away that it's not like it's just. There we go. That was a pretty good one.